Calculus, video 54, optimization, example 3. All right, this time you are in a kayak, 0.8 miles perpendicular to the shore. Actually, let me zoom out here a little bit so you can see the entire problem on one screen. It's a little bit long. There you go. So feel free to pause the video and write down the problem. Okay, so you're in a kayak, 0.8 miles perpendicular to the shore. You can kayak back to the shore at 2.5 miles per hour. And you can walk along the shore at 4 miles per hour. So in other words, it's faster to walk along the shore than it is to kayak back to the shore. You want to get to the snack shack. So you're hungry, you want to get to the snack shack in the least amount of time possible. The snack shack is 2.0 miles from the point on the shore perpendicular to your kayak. So it's along the shore. The snack shack is also on the shore. It's 2.0 miles from the point on the shore perpendicular to your kayak. This is a lot of information. How far along the shore from the point perpendicular to your kayak, from that point perpendicular, how far should you land to minimize the time to the snack shack? Okay. Seems like a complex problem. There's several varieties of these. There's a cost one where, like, if you're have like an oil rig out in the ocean, and there's a certain cost for getting pipe to the shore. There's a certain cost for getting pipe along the shore to a refinery. At what angle should you build the pipe? It's the same kind of a problem as this one. Let's draw a picture to analyze what's happening here. So we are assuming that our shoreline is straight, at least, basically straight. So here's the shoreline, and here is you in your kayak. All right, so there's your kayak. What we're saying is the distance from the kayak to the shore is 0.8 miles. You're 0.8 miles from the shore in your kayak, perpendicularly. So that's the point we're talking about. That's the point perpendicular. It's on the shore, perpendicular to the kayak. From there, from this point, you have a snack shack somewhere along the way here. Here's your snack shack. All right, snack shack. On the shore. The question is, how should you go from your kayak where you are to the snack shack to minimize the amount of time it takes to get there? I didn't write the 2 miles, right? So from here to the snack shack is 2.0 miles. The part about this that's tricky is you can walk along the shore faster than you can kayak back. And so let me just kind of give you some possible route options. One route option is the longest distance. If you go straight from where you are to the shore, straight there, right? You take that distance, how long it takes you to get to the shore, and then because you can walk faster than you can kayak, that means you shorten the amount of time you're kayaking and you're walking for a longer distance, and you do some sort of path that looks like that. The good part about that path is you're minimizing your time kayaking, which is your slower speed. You're maximizing your time walking, which is your faster speed. However, it's the longest distance that you could go. Okay, let me give you a path number 2. We'll do this one in orange. Path number 2 is you kayak all the way straight to the snack shack. Okay, the bad part about that is you're not spending any time walking, and so you're using all your time in your kayak going the 2.5 miles per hour, not using the faster walking at 4 miles per hour. However, look at the distance. The distance is much shorter. Therefore, you're going a shorter distance, even though you're not going as fast. Is that overall faster than going the longer distance? Or perhaps it's somewhere in between. Maybe you cut off some of the distance here but you're also spending some time walking here. It's less distance than the green, a little bit more time kayaking, a little bit less time walking than the green, but less distance. It's longer than the orange, but you spend more time walking, which you do at a faster rate. Right? And so is the one that makes the shortest time straight to shore in green here and then walk over, because you can walk faster than you can kayak, straight from the kayak to the snack shack, all kayaking, no walking, shorter distance, but you're not using the faster walking, or somewhere in between? That's the question. Okay, let's add a little bit more to this. Let's assume that it's, not necessarily assuming that it's somewhere in between, but if it is somewhere in between, we need to be able to write what those variables are. So I'm going to see if I can take off the green line here. And let's see if I can take off the orange line. Okay, let's assume that there is some distance x right here. Some distance x. So x would be the distance where from perpendicular to where you would land the kayak. Right, that would be the distance x. The remaining distance would be what? The remaining distance to the snack shack would be, well, the total distance from perpendicular to snack shack was 2 miles. You're landing a distance x along the way, therefore what's left would be 2 miles minus x, right? Minus however far you landed there. So we got a few variables there. Now, x could be 0, and if x is 0, that means you're going straight to the shore in that perpendicular distance. X could be 2 miles. And if x is 2 miles, that means the kayak is going straight to the snack shack without stopping on the shore any time in between. So we know that by this drawing, x is somewhere between 0 and 2. That's our constraints. What we want to do is to minimize the amount of time. Okay, so we need to set up a time equation. We need to set up some sort of a time equation because we are trying to minimize time. And one of the reasons in this case that students get this one wrong is they try to set up a distance equation. And we're going to use distance, yes, but we're minimizing time, so we want to set up a time equation. Go back a minute ago, I was talking about like the cost of building pipe and laying pipe in order to get from oil rig to oil refinery. In that example, you're setting up a cost equation, not a distance equation. So similar idea here. Okay. If you want to set up a time equation, there's two things we have to look at. There's the time that you would spend kayaking. Let's call that time 1. And then there's the time that you'd spend walking. Let's call that time 2. So our time equation, T, can be thought of as the time you spend kayaking, time 1, plus the time you spend walking, time 2. There's our time equation. Okay, let's think back here. We know that distance equals rate. Oh, it needs more room. Distance equals rate times time. But we're trying to set up a time equation, so let's solve for time. We know that time is equal to distance divided by rate. So we have time 1. Time 1 is its distance, let's call it distance 1 divided by rate 1. And time 2 will be its distance, d2, divided by rate 2. And so we can take time 1, find out what that is, plug that into our equation, and time 2 and plug that into our equation, and possibly, hopefully, be in terms of one variable. My guess is we will try to make this in terms of the variable x. Okay, so let's see if we can do this. Time 1. That is distance 1 over rate 1. So this is kayaking. Right? Time 1 for kayaking. What is the distance that we'll spend kayaking? Well, the distance that we'll spend kayaking is that first section, that first pink line from kayak to the shore. Time 1, also maybe call this D1 here. So we need to know what that distance is, and we'll take that distance and divide it by rate 1. Well, I know rate 1 because I know that we can kayak at 2.5 miles per hour. So 2.5 is the kayaking rate. We just need that distance, D1. Well, D1 looks like it is the hypotenuse of the right triangle, with side 0.8, other side x, hypotenuse D1. So we can see that D1 is equal to D1 squared is equal to 0.8 squared plus x squared. In other words, D1 is the square root of x squared plus 0.64, 0.8 squared, 0.64. So we have D1 is the square root of x squared plus 0.64 divided by 2.5. That is D1 divided by R1, that is time 1. Or maybe we write it like this. 1 divided by 2.5 times x squared plus 0.64 to the 1/2. Okay, very good. Now let's see if we can find T2. So this would be walking. Time 2. Time 2 will be distance 2 over rate 2. Well, rate 2 I know. I'm walking at 4, or you're walking at 4 miles per hour. What is distance 2? Well, distance 2 is right here. Distance 2. Distance 2 is the part walking. That is the 2.0 minus whatever the x value was back here. So distance 2 is simply 2.0 minus x. Or if you write it out, 2.0 divided by 4.0 is 1/2, or 0.5, minus 1 divided by 4 is 0.25x. Right, so 2.0 divided by 4.0, 0.5, 1 divided by 4.0, 0.25. So 0.5 minus 0.25x, that's times 2. Okay, so overall time it will take us is time 1 plus time 2. That would be time 1, 1 over 2.5 times x squared plus 0.64 to the 1/2 plus time 2, 0.5 minus 0.25x. Okay, this is good. We now have a time equation that we want to minimize, and it's all in terms of one variable. Okay, so we can take the derivative. T prime is equal to 1 over 2.5. We'll bring down the 1/2. We will get x squared plus 0.64 to the negative 1/2. Chain rule times 2x. And then minus this 0.5 derivative is 0, and minus 0.25x becomes just minus 0.25. We want to know when is this thing undefined, and when is it equal to 0. So let's see, when is t prime equal to 0? It's equal to 0 when we have, 1 over 2.5 times 1 over 2. Well, actually, let's do this. This 1/2 here will cancel out with the 2 here. And we'll rewrite that as 0 is equal to the x I have from here, 2.5 denominator. And let's take this x squared plus 0.64 to the negative 1/2 and write that as a square root of x squared plus 0.64 in the denominator. Minus 0.25. Okay. So setting it equal to 0, we have, adding 0.25 to both sides, 0.25 is equal to x over 2.5 square root x squared plus 0.64. Let's go ahead and multiply that through. Multiply both sides by 2.5 square root of x squared plus 0.64. So I have 0.625, so that's 2.25 times 2.5, 0.625 square root x squared plus 0.64 equals x. I need to get rid of the square root, so let's square both sides. Remember, squaring, you square entire sides, not individual terms. So I'm going to square the 0.625. I get 0.390625. Times the x squared plus 0.64 equals x squared. All right. Distribute. So 0.390625x squared plus, oddly enough, 0.25. 0.64 times 0.390625 is 0.25 equals x squared. So subtracting the 0.390625x squared, I get 0.25 equals, that's got to be like 0.600 something. 1 minus 0.390625 is 0.609375x squared. And we're getting there. Dividing both sides by that, 0.609375. I'm getting 0.41026, I'll round a little bit here, equals x squared. Take the square root of that, 0.641. Okay, let's go back and think about what was x. X is 0.641. In other words, what we're saying here is we should kayak to a point at 0.6, let's just call it 0.64 miles along the shoreline, and then walk 1.36 miles the rest of the way to the snack shack. Okay, did that answer our question? How far along the shore from the point perpendicular to your kayak should you land? That is our x value. To minimize the time, that would be about 0.64 miles from that point perpendicular to the shoreline from our kayak along the shore to minimize our time. So it was, in fact, a point in between that ended up minimizing the time. So answer there is 0.641 miles.